This is a tutorial for lift formula problems 11 through 15 from the worksheet for aerodynamics. A review of the basic lift formula. Lift is equal to the coefficient of lift times density ratio times velocity squared in knots times surface area of the wing divided by 295. And so then the other formulas used are load factor, and load factor is equal to lift over weight, and load factor from bank angle can be found with the formula 1 over the cosine of the bank angle will give you the load factor per bank, independent of airplane type, speed, doesn't matter. A specific bank angle will give you a specific load factor. We're also going to use the categories, normal, utility, category aircraft, but these are the load factors that these various categories of aircraft are built to. So normal categories 3.8 Gs, utility 4.4, acrobatic 6, and transport categories 2.5, and these are all positive load factors. Negative load factors are less. Picking up at problem 11, we want to figure maneuvering speed for this normal category airplane. Start with the lift formula, solve it for velocity, so simply take that lift formula, solve it for velocity. Then we're going to simplify that formula so that we don't have the square on the velocity. So that puts the square root on the rest of the formula. And then we add in this load factor. So what would the stall speed be at this airplane at a load factor of 3.8? So 3.8 times the weight of the airplane will give us the lift that the wing has to generate. So at what speed will this airplane stall? So then it's simply a matter of plugging the values in, the known values, into the formula and solving it. And the stall speed at a gross weight of 2,917 pounds, pulling 3.8 Gs, so the weight is really, the lift generated by the wing is really 3.8 times 2,917. What speed will it stall if it has a CL max, coefficient of lift max, which equates to the angle of attack at which this wing will stall of 2.4. If you have a wing area of 199 and assuming density ratio of 1, which is sea level, VA is going to be 83 knots on this airplane. Problem 11 is identical to problem 12, except for the category of airplane, which is a 4.4 G airplane, or certificated in the utility category. So we would anticipate that the stall speed would go up, and so everything is worked the same as the previous problem, except we use 4.4 Gs instead of 3.8. So the wing would have to generate more lift, and the stall speed would, or the maneuvering speed would go up accordingly. And so that calculates to 89 knots. This is a change in speed for a change in weight to give you the same conditions. In this case, it's VA. So we've given a published VA of 120 knots at a gross weight of 2,163 pounds. what will your new VA be at a lesser weight? You would expect that VA to go down. Start with the lift formula, cross out everything that we don't need. Uh, Move all of condition 1 to the left side of the equal sign and condition 2 to the right side. So the knowns, we have lift under condition 1, which is the gross weight of the airplane divided by the velocity for that particular weight, and we're given the new weight. What would the new velocity be for the same conditions for the same weight? And so we're going to solve that for the second velocity, simplify the formula, and we wind up with the new weight divided by the old weight times the old velocity. Plug in the values, the known values, and we wind up with a new VA at the lighter weight of 109 knots. So this is a very important manipulation of the lift formula to figure new VAs for new weights. This is just a load factor problem. You have 1,747 pounds. Since load factor is equal to lift divided by weight, we could figure lift then is equal to weight times load factor, or 1,747 pounds times 3.7 G's. So at a load factor of 3.7 G's, if your gross weight was 1,747 pounds, your wing would be producing 6,464 pounds of lift. This problem is a two-step problem. First thing we need to figure out is how much lift the wing is actually producing at this, given these conditions. So we just take the lift formula, plug the known values in, and we have that wing is producing 12,190 pounds of lift. Then we go to the lift, or we know that load factor is equal to lift divided by weight. Therefore, weight must be lift divided by load factor. And so it's a normal category airplane, so the load factor is 3.8. So that airplane in that configuration is weighing 3,208 pounds. Because at a load factor of 3.8, the wing is producing 12,190 pounds of lift.